It is 3 o'clock. Let's get started. So welcome everyone to our distinguished lecture series seminar today. The DLS seminars are the main high-profile scientific event of our institute, the Max Planck Institute for the Science of Light. It's a means to engage the most important and influential colleagues in any area of the science of light. And also today is no exception to this. But before we get to our speaker, I want to mention a few technical comments. The seminar is being recorded, so please be aware that by participating from this point on, you implicitly agree to doing this. And the second point is that generally we ask that your mics are turned off during the presentation. If you have a question, please type the letter Q into the chat space, and then I will ask you to unmute to ask that question, and then you can have a discussion with our speaker. And for very urgent questions, I guess we could do that throughout, but most questions should then be asked towards the end. So now on to today's presentation. It's a great pleasure to welcome Christine Silberhorn, who hardly needs an introduction as she's no stranger to the MPL. Christina did her PhD in Erlangen at the university in 2003, had a short postdoc stint in Oxford, came back to Erlangen before actually starting her own independent Max Planck research group on integrated quantum optics at the Max Planck Institute for Quantum Optics in Garching down the road. She took this group back to Erlangen in 2008 to continue here for 2 more years before becoming a professor at the University of Paderborn in the year 2010, where she's still at the moment. I guess Christine is best known for her research on the development of tailored integrated quantum devices and systems for using quantum computing and quantum topology, so something that is of great interest to us. Her research has been honored by several important recognitions, such as Gottfried Wilhelm Leibniz Prize in 2011. She got an ERC Consolidator grant in 2017, is an elected member of the Leopoldina, and is also fellow of the Optical Society of America. So I'm very much looking forward to your presentation, and without much further ado, I want to give you the stage. Christina, thanks for joining us today.
Well, thank you very much for the introduction, and let me start my presentation. I hope you all do see now my slides.
Yes, looking good.
Okay, thank you very much for the introduction again, and also for the opportunity to present my research. What I want to be talking today about is nonlinear integrated quantum optics with pulsed light. Now, this is a rather descriptive title, and here you see also one of the devices which are fabricated in our clean rooms and used in our quantum optics labs. But let me get started in giving you a little bit more of a broad view and motivation what we are doing in our group. Actually, we are looking at quantum networks, and I like the term quantum networks because quantum networks for me are kind of a model system. They are a model system for complex, large-scale structures. And of course, some of the things is obvious what we want to aim for it. For example, the quantum internet, and this is kind of very well known for quantum communication. But quantum networks can stand for much more. You can think about studying transport phenomena or also brain phenomena, brain networks, and so on. And one of the motivations from the fundamental point of view is that we want to understand what does such networks make quantum, and what is the role of quantum physics. And I hope within this talk, it will become more clear that this question is not really an easy one. Now, as you well know, I'm coming from the photonics community, and there the same topic can be viewed a little bit differently. What we're trying to do these days is to look at multi-dimensional photonic qubit systems. And this is kind of the same thing, just describing it differently. Why do we want to do that? Well, one thing was already mentioned, it's quantum computation, quantum simulation, and I will come back to that, well, basically in the next slide, where we have seen great advancement in the last year. The other thing where multi-dimensional systems and multi-parameter becomes important is quantum metrology. And last but not least, of course, quantum communication, talking about photons, is always an important topic. there, high-dimensional information coding also have great benefits, which we're also interested in. And this is kind of the framework of the research and why we do the research from a fundamental, but also from an applied point of view. Now, let me say a few words about photonic quantum computation, because I won't go into detail in my talk about that. Nevertheless, this is a topic I'm highly interested. Optical quantum computation, I think, started in 2001, where people really saw that we can do a lot of things with linear optical systems, linear optical quantum computation, and the famous proposal of Neil LaFlamme-Milburn. Now, we had to learn over the years that this proposal needed a huge amount of resource, and we have become less ambitious. And this is the time where it started that we talked about quantum simulations and quantum walks, and we also have contribution in this area. Now, I think the next really major push in this direction was the topic of boson sampling. What is that? Well, people realized if you just have a linear network which implements a so-called hard random matrix, and you can feed these linear networks with single photon input states, that you can't computate what's coming out of the distribution which is resulting in that. This was quite a surprise, because it kind of shows that you can reach quantum supremacy, or quantum advantage, which I prefer to say, of a rather simple system, and it shows that quantum photonics can be rather powerful. And this is exactly the topic which I highlighted right at the beginning. In December last year, there was a great publication in China from John Wei Pan's group that they showed quantum computation advantage using photons. Now, this was interesting because up to that point, people always said, well, quantum computation and photonics probably will never work, but it shows that really we can scale up systems. Now, for me personally, an interesting point was that they actually didn't use the system of boson sampling I just showed you before, but they used a variant so-called Gaussian boson sampling. What did they do? Well, we have the same linear network, these hard random matrix, but they used different input states. They didn't use the single photon input states, but actually they used input squeezed states. And this was quite interesting for me, because the system to do that, we proposed together with EGOX groups in 2017. At that point, we realized that scaling the system to single photons will probably be really, really hard. On the other hand, producing single input states, squeeze states, is something which we can do rather straightforwardly in photonics. What you have to do is you have to look at the photon statistics, and this is what we did. We asked ourselves, what is happening if you replace the single photon states just by Gaussian states, these squeeze states, and looked what is the photon pair generation probabilities and how do the photon probability distributions look like. Now, this one advantage I emphasized already is that you have a really good scaling in terms of photon numbers. If you use these states, and you can really simplify the system at large. And this is also why they could show this quantum advantage. Now, then you have to ask what is really happening. So how does this computational advantage transfer? And there we are not looking at permanence anymore, but of Hafnians. But apparently they have the same complexity class in mathematical terms than the original proposals. And I should say, for me, this is quite exciting, because I know a lot of computer science people, now that this experiment has been performed, are looking at these things. And I think this is an exciting time for looking at such questions. Having said that, we didn't implement the experiment on our own, because it was obvious for me that in a group at university, we couldn't do that experiment. Now, before I keep going and go into detail in my research work, I would like to show you how my research group is composed of. The reason of that is that this is also showing the philosophy, how we pursue our research. Now, this is the Integrated Quantum Optics groups, which is located in Paderborn. And this group has several subgroups. First of all, we do quantum technology. And this is why I really believe if you really want to drive quantum science and photonics further, we also have to develop the associate technology to that. It might seem obvious to you, but actually it is not. There's only a few groups who really have their own technology these times. The technology we are working in the clean rooms, we are developing lithium niobate circuits, KTP circuits, and nowadays we have also started to use LNOI and want to tailor these devices for quantum applications. Then the next subgroup is called devices. There we have device design. So we know what kind of optical circuits we should build up. We give the modeling, and all the designs are done in the devices group. And this devices group also does the packaging. Here you see one example of that we really can have real practical devices, which is important for the applied side of this research. And last but not least, my group has also the quantum networks groups. And this is really where I'm coming from. This is the quantum optics side, where, this is called networks, where we do quantum walks and ultra-fast pulsed engineering, where we basically take the ideas from theory, from quantum information theory and quantum communication, and try to see what we can implement. You see, each of these groups has group leaders: Christoph Eigner for technology, Harald Hermann for devices, and Benjamin Brecht for the networks. With that, let me go to kind of an outline of this talk. What I want to present to you are different strategies for scaling photonic systems. And I will present them individually and will show you the experimental results of these different research lines. At the end, you can combine these approaches, but we're not there yet. These approaches are, on the one hand, integrated optics, and I told you already about this clean room work we do. It's time multiplex quantum systems because time is a very cheap resource. And last but not least, I will also show you temporal modes of pulsed light, how we can use these for information encoding. And so at the moment, it might be not obvious why this is also one strategy for scaling. It will become clear, I hope, during the talk. So let me get started with integrated quantum optics. And to be a little bit more specific, what I will be talking about is nonlinear integrated quantum optics. And there, let me start with a rather old review. This is from 1969 for Miller, Integrated Optics, an Introduction. Why do I do that? This is because I would like to emphasize that we're not starting things completely out of scratch, but actually we're building up on know-how, which is really established know-how, but we also need that. Now, the funny thing is, if you take this review and just add a few words, so instead of you talking about integrated optics, you add integrated quantum optics, laser beam circuitry, you put quantum circuitry, there you replace another laser by quantum. Sometimes you have to replace laser by photon source. And I think I don't have to tell you in this audience that this is not easy. But nevertheless, if you do that, then this review becomes all of a sudden very modular. And let me read the last sentence. If realized, this new art would facilitate isolating quantum circuit assembly from thermal, mechanical, and acoustic ambient changes through overall small size. Economy should ultimately result. This is exactly what we want to do in quantum optics these days. And I think I would like to emphasize, keep the ideas, but adapt them to quantum optics. This is a strategy for integrated quantum optics. Let me give you a little bit more of a modern view on that, which is about hybrid integrated networks. And this review is about a photonic quantum simulators. And it shows quite nicely how the community thinks about that. Now here, Asper Gutzik and Philip Balder kind of show that they have a photonic simulator, which consists of a source part, a circuit part, and a detection part. And it's an integrated circuitry. Now, one thing I would like to emphasize there, this part, what is called circuit, is linear, it's just beam splitters. While this part where we have source, this is the nonlinear part of it. Now, why do you implement it in that way? Well, using integrated optics for quantum optic experiments has many advantages. All of a sudden, you have many spatial modes available and they're controllable. You have the interferometric stability of large optical systems. You can have compact devices, miniaturization follows. Easy operation, well, it depends what you call easy. And you need, and this is kind of one prerequisite, high efficiencies. Now, if you look into the literature, integrated quantum photonics has become really a buzzword, and it's a whole community, a whole field on its own with companies coming up and so on. Most of the things, however, and this is kind of pioneering work from Bristol, looked at the linear part. And this is, as I said, just a few examples. You can have much, much more these days, Bristol, Rome, Oxford, where people really implemented different quantum optical systems. But if you look at that, the sources were always outside. It's just a circuit, linear circuitry, which is integrated. Now, what we have been concentrating for more than 10 years now is to develop this nonlinear part. And there the field is much less advanced. And the reason is that you can't have customized devices, but you have to build them on your own if you really want to have good performing devices. This is kind of the vision we have of our platform. This is a lithium niobate platform, which should have minimized decoherence, so very low loss waveguides. This is why we're using quite frequently very well-established technology. We have the stability and the scalability. The big advantage of having a Chi2 nonlinear material is that it can have very efficient photon pair generation based on the Chi2 nonlinearity, and equally important, fast photon routing, such that they can have fast electro-optic switches. This is actually a topic which quite frequently people just don't mention, but this is, I think, a really important ingredient if you really want to make progress in this field. The vision is that you have different functionalities on a single chip, like photon pair generation, phase shifters, single photon conversion, polarization control, and even detectors can be put on this platform too. And you want to implement rather complex circuits on that platform. Now, the toolbox of these integrated devices are, on the one hand, you have passive routing, generation and storage, photon pair generation, quantum memories can also be included, active manipulation, which can be only done in Chi2 materials, and their lithium niobate is kind of famous and used in commercial applications a lot, like phase shifters, polarization transformers, space switches. And last but not least, you also have to care about the interfacing, fiber waveguide coupling, that you really can implement them in networks, or mirror coding, such that you can build up resonators. Now, these components, most of them have been developed for classical optical applications, but now we have to tailor and redesign the optimizations for quantum applications. Is exactly what we do. Now, I give you some view on just the examples which we do, but I can't talk about all of them, and I will only say one example, but at least want to mention it. So over the years, we have built up a plug-and-play single photon source with very high efficiencies, noon state photon source, which is an entanglement generation source with a new concept of high photon pair generation within a directional coupler. The generation of polarization entanglement, which is kind of, call it a queer-like source, free photon generation with cascaded nonlinearities. We have built optical squeezing using waveguide resonators. We have implemented a narrowband photon source, which can be ideally connected to memories. Waveguide resonators with integrated modulators. Here you see that we combine modulators with active electro-optic elements. And the newest topic we are studying is fully integrated quantum interferometers, where we also have our first results. Now, the experiment I want to show you is a fully homomantle interference chip, experiment on chip, which is the most advanced circuit we have implemented so far. So let me just talk briefly about homomantle interference, so I'm aware that you know that. What we are studying it is that two photons imping on a 50-50 beam splitter, and because of destructive interference, the two situations where both photons leave at different ports interfere destructively. Thus, the photons always leave together at one output port. This homomantle interference is a measurement-induced nonlinearity. It's a fundamental quantum property. It's the basics of linear optical quantum computation and quantum networking in general. The experiment of these famous homomantle experiments is the following. You have two single photons impinging 50-50 beam splitter. You introduce a delay, and depending on the delay, you look at the coincidence count between signal photon detector A and B. If there's no delay, we have the homomantle interference experiment. However, if there's a delay, you have this distinguishability and you kind of don't get the full interference. Now, how do you implement such an experiment on an interferometer? What we did was a monolithic integration of a parametric down conversion source of type 2, which had two different polarization, a two-photon interferometer, and a time delay, where the electro-optic control allowed us to do polarization conversion, implement a fast optical delay, and have a tunable beam splitter at the end. I would like to walk you through the experiment. So a pump photon decays in the PDC section in signal idler photons, and the first thing we do with the polarization converter is to swap the polarizations. I will tell you in a minute why we do that. Then we have a polarizing beam splitter, which separates these two photons deterministically into different paths. And then you see this device on the top, which is again a polarization converter, but this time segmented, such that we can switch the polarization at different points in the chip. Now, if we switch the first segment, this is a 50-50 beam splitter, we see just the homomantle interference as I explained you before. However, if we switch this beam spread at a different segment, due to the birefringence of the nonlinear material, we introduce a time delay because the two photons travel at different speed. And then we expect that we don't see an interference. So this is the theory which we expect, depending which segment we switch. We expect that the coincidence probability will be varied, where at this, if we switch segment 2, there is no distinguishability between the photons, and there we introduce distinguishability. I also told you that we have to switch the polarization from the beginning. If we don't do that, then we always have a time delay between signal and idler photon, and we don't get this indistinguishability at all. Now, this is experimental data, and you see that it fits quite nicely. So depending, this is really which segment we switched. We see the interference. If we haven't switched it, we don't see an interference. This is experimental data. We can replot that now. And then you see that here, we recalculate how much delay this caused, these different segments, and look for the coincidence rate. And you see nicely the homomantle interference chip, and if you interference dip, and you have asked what kind of visibility, you have really good visibility of around 49%, and the time delay we can achieve is around 12 picoseconds. And this is actually the device, how it looks in the lab. And this kind of shows you that, yes, we can produce all these different devices which are needed for quantum technology these days. With that, I would like to switch topic and show you the second topic, how we want to scale up system. And here you see that we are now returning to not integrate devices to standard quantum optics experiments with a lot of things on, well, on an optical table. Time multiplex quantum systems, we look for studying quantum simulation experiments or to study and understand what is the coherence of the system. And the best way of understanding that and studying is to look at random versus quantum walks. Now, random walk is something which I guess you're very much aware of. So this little guy doesn't know where he should go anymore. He throws a coin, and depending on the coin, he does take a step to the left and the right. But that, if you ask which kind of distribution results at the end here, you get the binomial distribution, which is well known from mathematics, and it corresponds in physics to diffusive propagation. And this is a probability distribution which you expect, where the variance is proportional to the number of steps. Now, if you make this system quantum, you introduce a quantum coin, which is a two-dimensional Hilbert space, which is coupled to the space degree of freedom. Now we do the kind of the same experiments. We throw the coin, which means in this kind that we kind of have two states, and these, depending on which kind of polarization, this horizontal or vertical, we do a step to the left and the right. And then the evolution is kind of followed by these beam spread interactions. So at every peg here, we have a beam spread interaction, and we ask what is kind of the distribution of these quantum walks. It looks completely different because the coin is a quantum state. We have superposition principle, and if you have the coin kind of defines this evolution, but if you have a specific Hadamard coin, you get the ballistic distribution, where you have much broader spread of this distribution, and the variance pairs with a square number of step size. And if this kind of quantum behavior becomes much more pronounced, if you go more and more step size, this means larger and larger systems. What makes this quantum system quantum here? And I would like to emphasize that. Here we assume that we are starting with classical photons, and the classical light is kind of a particle picture. Going to the quantum domain means that we are going to look at the wave-particle dualism and looking in these superposition states. And this is how we understand the coherence property is kind of the quantum property in this system. Why is that interesting? Well, random walks are used in information science and also for simulation in a lot of different ways. Classical processes like Brownian motion that can be simulated with that, biological systems, here deer wandering, and in information science, if you ask what's behind the Google search algorithm, it's actually also a random walk. And the idea then is, well, if you go quantum, you can model also other systems like semiconductor physics systems, quantum biology, and of course, this is where also the motivation comes, quantum computation and quantum simulation. The question is, how can you implement such a system efficiently? And the way we pioneered was by using time multiplex quantum states. So this is a setup where this is a double loop systems. Here we have an input state which comes in, which is a light pulse. And well, ignore that for the moment, but it's an electro-optic modulator. And then we implement the coin states by polarization. And this is a half-wave plate. And we have a double loop structure, and we loop the system back. Now, let me show in detail how that is. We are starting here, and we come in with an optical pulse. We have a half-wave plate, which is kind of the coin space. Now, we're in the system at that point where we have introduced a polarization-dependent delay. If we have vertical polarization, the pulse travels the upper path, where the horizontal the lower path, and you see in that way that the relative shift in time corresponds to a step in position space. So we've introduced the first step. We are here at this position, and we kind of go back into the same system. We start now with the things with the two pulses. We do the same system again, and what you see there is that interference occurs for the second round if you have first take the short and the long path, or long and short path. And it turns out that this system is exactly modeling these quantum box systems. And it's a very efficient system because we use the resource time to implement that. Now, if you replace your half-wave plate by an electro-optic modulator, you have the additional advantage that you have a fully reconfigurable system. So we can impose on every position a phase to our will, and really can start dynamics by that. This is one of our early experiments, and this is actually experimental results. It's a quantum walk over 28 steps that would correspond spatially to 406 beam splitters and 29 detectors. And you see here very nicely that the experiment in theory in gray and blue coincide very well, the quantum theory. And this was kind of the starting point for us to build up rather large optical interferometers. And you see that they are extremely homogeneous. So if you try to do the integrated optics, you will have a hard time to really find such good quality of walks. This is a big advantage of our system. Now, again, I don't have the time to show you all the work we did in these things, but we exploited this circuitry and this time multiplexing for all kinds of different systems. We studied in 2D quantum walks. We studied the impact of decoherence and losses. We looked at percolated graphs. We did graph engineering, state transfer. We also implemented systems which come to the motivation from semiconductor physics and implemented topological invariants, measured them. We looked now at quantum box with 4-dimensional coins, and we also looked at measurement-induced dynamics. And I should say all this was still done with coherent light. It's quite amazing that you can even simulate measurements in that things. We had good fun with that, but we always got one question: what makes a quantum system quantum? And it's true. I guess many of you have realized that this is just an optics experiment because we used a coherent light pulse at the single photon level, but still you could explain that just as an optical system. If you really want to go really quantum in the sense of a quantum optics experiments, you have to use not only a single particle, but many particles. So my way of viewing that is to say, well, we have to cross another boundary. We want to have multi-particle effects. And this is really what we did recently. How do you do that? Well, we implemented quantum box now with photon pairs, such that the quantum nature of these systems becomes more prominent. These are technical details for the experts. The source we had to implement was rather tricky. I had to use a type 2 parametric down conversion source. It's an engineered source for pure single mode photons, and it had to be in the picosecond regime. And this is kind of one of the parameter regimes which is really hard to implement. But here what you see, this is again the network we used all the time. This is a detection, which is also standard. Now we have also method to input and output couple them deterministically, and the source which you combine with that. And what we wanted to show is the first experiment is really to see this interplay between the different coherences, between quantum coherence and classical coherence, or in other words, between quantum interference and classical interference, or in other words, between first and second order correlation functions. And we did the following experiment. We synthesized single photon time pin superposition states. So here you see that we have, these are two different cases. our state preparation, which is heralded single photons. We programmed our circuit, which you see in blue, such that at the output, in this yellow thing, that we had superposition states. On the one hand, it's always the two blue input photons at equal height, and also the right have very equal height. And here, in the first case, we didn't have a phase between those two systems. In the second case, we have also a complete coherence, so first order coherence. But what we changed in comparison to the first case is that we had a phase of 180 degrees, such that the photon wave packet of the second photon looked differently. And now you can do the following experiment. You look at the quantum interference of the blue photons interfering delocalized with the red photon, and looked for coincidence counts in both cases. And looking at coincidence counts, you can now do either locally or globally. Locally basically means is that I ignore that there's a second part, and I look here at coincidence counts in a time-resolved fashion, and I just look coincidence counts versus single sounds for both of these arms individually. And what you get in both cases is nice homomodal interferences. Now, interestingly, you can do also different measurement, which is a time packet detection. Here, we kind of look also again in a global way on coincidence counts, but now we don't care whether the photon count is in one of the blue or one in the red, and we just take these counts together in both cases. What will happen in this first case, because the wave packets are identical, we get perfect quantum interference back. However, in the second case, these wave packets are kind of orthogonal to each other, and there's no quantum interference in this global picture there. What does it tell us? It tells us that the first order coherence kind of can steer the second order coherence properties. This is interesting because it shows you the interplay how classical coherence can control quantum coherence. And moreover, it might find applications for quantum communication protocols where you really can get very distinct features. And I think it also highlights that scaling up photonic systems, the crucial ingredient are photons. And this is why I liked it a lot from a fundamental point of perspective. With that, I would like to switch once more the topic, because I promised you to show 3 different strategies for scaling up system. In the remaining, 10 to 15 minutes, I would like to show you our work on temporal modes of pulse light. What is that? So I first want to explain what is temporal modes and what is temporal mode encoding. It's a time frequency encoding, and I want to be a little bit more detailed. If you encode information and we want to use a higher dimensional alphabet, we can either use time, and you see that here on the left, where every different timestamp, like the time beginning, means one letter of the alphabet, and we can do the coding there. As an alternative, you can say, and then in this case, the frequency is completely undefined. You could do the opposite, that you say, well, I'm encoding my information, the frequency to mean, and the time is completely undefined. Or you go somewhere in between. And this is what we call pulsed temporal modes, and which we have been pursuing for several years now too. Now we do an encoding where these pulsed temporal modes, they kind of are overlapping, or on top of each other in time and frequency, and kind of span, they always live in this time frequency space. If this looks strange for you, just think of them like spatial modes. There we are very used to that. If you look for Hermite modes, it's exactly the same mathematical concept. Why would we be interested in such an encoding? Well, it's a high dimensional alphabet, like spatial modes are. And the advantage of this high dimensional alphabet, it's completely compatible with waveguide devices and fiber networks. And they should also be not influenced by dispersion. So they are really ideal for doing information encoding for communication properties if you want to have a high dimensional alphabet. The only problematic thing is how can we measure and manipulate them? Let me explain a little bit more in detail what I mean by that. So if you're talking about modes in general and frequency modes, quite frequently in the basic quantum optics lecture, you learn, you have your harmonic oscillator, you introduce a field quantization volume, and then you have a monochromatic frequency and say, okay, fine, now we don't care about the modes anymore. Now we quantize things, and this is how field quantization works. Now, this is not going to work because if you have a monochromatic frequency, you can immediately see by a Fourier transform that you have something which has an infinite time. And for quantum communications, this can surely be not the state you're looking at, because you need something which is also constrained in time. And then if you want to ask, what should I use instead? You will immediately come to the concept of the temporal mode creation operator. What you kind of do is you define a wave packet, which is the coherent superposition of different frequencies where this photon kind of lives in. Before you transform this system, you get something which is also constrained in time, and you have a nice mode. Well, this is the temporal mode of a Gaussian mode. And what we did, we introduced the envelope function. However, if you have accepted that, it's also rather quite natural to define modes by their pulse shapes. And this way you can define field orthogonal temporal modes. So every envelope function here defines a different mode. And because the envelope functions are orthogonal in this integral form, the modes are also orthogonal to each other. And this, we have introduced the basis transformation in these broadband pulse modes or temporal modes. And then the next step, you kind of don't have to care about anymore. Instead of thinking of different individual frequencies, well, you just think of different pulse shapes, and you can work with them in terms of information encoding completely equivalently as if you had different monochromatic frequencies, or also conceptually if you had different spatial modes. Note again, and I will come back, that these temporal modes are kind of living in the same time frequency degree of freedom, and we kind of have to sort them later on. Now, the control of these temporal modes and the motivation to have them is the second one, is that parametric down conversion is kind of ideal for this temporal mode encoding. If you do an engineered source, and I will show you in a minute how you can do that, you can have a state preparation of this parametric down conversion in such a way that you can completely control this temporal mode Hilbert space. If you control it such, and you have very specific dispersion properties, that we have group velocity matching, a Gaussian pump pulse will decay into Gaussian signal and idler pulses. And the tool to develop that is that you have a joint spectral amplitude which decorrelates. This is again for the specialists. This is energy conservation, momentum conservation, and you kind of find specific conditions that you get these nice decorrelated states. If you're in this scenario, then you can start to introduce pump pulse shaping. And then by shaping the pump pulse, which you can kind of doing with a software approach, you're creating Hilbert spaces which are higher dimensional, and you really can create it to your will with different joint spectral amplitudes, such that state preparation in these temporal modes can be easily done. The second ingredient, and I told you already, is then the manipulation detection. And there we invented the system of the quantum pulse gate, where we use some frequency generation, a very specific some frequency generation transfer function, such that if you put these input states there, we can have this some frequency generation with different pump pulses again. And depending on the shape of the pump pulse, we can select which of these modes we address and frequency convert, and all the others are left out. These two things are the ingredients to now build on these higher dimensional Hilbert spaces and build a scalable system on these temporal modes. Now, how does all this work? The parametric down conversion, or what is the physical background of the system, can be understood for pulse systems in terms of Schmidt decompositions. And this is now really going into detail about the thing I just told you. So if you look at a standard parametric down conversion system, due to the nonlinear interaction between the pump pulse and the nonlinear waveguide, you get photon pairs generated, but typically there will be a strong correlation because of energy and momentum conservation. Now you can decompose these systems back into temporal modes, and this is the concept of the Schmidt mode basis, such that you create a multitude of these Schmidt modes, but they're not normally, you don't do that in a very controlled fashion. This is actually a problem if you want to use these parametric down conversions in spatial mode encoding scenarios or in networks, if you use spatial modes. So you have pairs of pulse temporal modes, and this is what you kind of have to deal with. Now, people came up with the concept of source engineering, and this is what I just showed you beforehand. You design your system very specifically where these correlations are kind of eliminated, and then you really can have these joint spectral amplitudes with no correlations present. And the scenario I just showed you that you have two nice pulses. And this is important that you have very specific waveguide properties for that. Now, these sources, we use them also in our lab quite a lot. They are ideal PDC sources for integrated networks with multiple spatial channels. It's pulse light that you can have synchronized events, which is important, for example, for non-Gaussian state preparation. They have a very high purity, high brightness, and they're also pure squeezed lights. The ones I showed you, you need for Gaussian Boson sampling, for example. Now, in this research line, we are going through a different route. So we are starting again of these specific waveguide scenarios. And I told you already that now we introduce pulse shapings that by just changing the pump light, we can tailor our Hilbert space the photon pairs are generated at. That's quite nice because we can directly use the temporal modes to now play with that larger dimensional Hilbert space. And this is at the moment work in progress in my lab, where we have full control of the state preparation in these temporal mode bases. The second step now is we have to sort these things. These temporal modes have to be sorted out, as I also explained that already. And the way to do that is the quantum pulse gate. For that, we need a very specific transfer function, which is a narrow function for the signal function which comes in the converted system. And it's designed such that, similar what I showed you with the engineering of the parametric down conversion, you do the engineering of a some frequency generation. And in doing so, you really can address only one single temporal mode, which has to be adapted then to the modes which you're generating. Now, a little bit more detail. The realization is scrupulously matched some frequency generation, and the transfer function is such that the efficiency of the some frequency process is just the integral of the input field with the pump field, such that you really have the conversion in these modes. The technical requirements for that is actually we need one of our home-built periodic lithium niobate waveguides again with specific polling periods. What is quite convenient for us is that the input light is around 1550 and the pump light is at 860, which is ideal for really doing shaping of a TISAF laser system. What we did show first is the selection of arbitrary temporal mode and time and frequencies superposition states, such that we could reconstruct the POVM elements or the measurement basis of a 7-dimensional material unbiased basis. This works pretty nicely. And what it shows you is that actually for quantum communication systems, we have the tool available for doing already 7-dimensional encoding with these temporal mode systems. Now, the next step is, can we combine it with quantum light? And here, what we did is we implemented one of these sources I presented to you, where this is now the single mode. And we combined it with the quantum pulse gate and did a tomography. This first is kind of the measurement of this joint spectral intensity you need to show that. And we analyzed that with our quantum pulse gate, and we could verify quite nicely that only one temporal mode is really present. Then we programmed our PDC with different pump modes such that we expected exactly 2 modes to be present. And here you could see that we also could confirm that. So basically, this shows that yes, we have the measurement tools, but we also can combine it with quantum light already. And for us, it's again now the stepping stone to keep going, to explore this system further for quantum communication applications, but also for simulations, which we also work, which is in progress at the moment. In the last minutes, I would like to show you another topic on these quantum pulse gates, because it turned out we developed that in the framework of quantum communication systems. And then it seems, or we realized that it's also a beautiful tool for quantum metrology. And the applications we have is the parameter estimation for incoherent light. And this is a system which has been proposed by Zhang et al. In 2016. And the question is the following. We have 2 incoherent light sources, for example, stars, where we want to estimate the separation of both of them. It's incoherent light, and you ask, how well can we estimate this distance as x between them? What you can do in space, you can of course also do in frequency and time. And here again, so typically these 2 distributions we want to distinguish. If they're coming closer and closer together, you can't distinguish them anymore because of fluctuations. And you can analyze how well you can do that. And this is the so-called Kramer-Rao band. So this is the separation. And this is the variance which you can get from that. And if you do intensity counting, quantum information theory tells you that this variance goes too large, and you basically can't distinguish the distance anymore. This is not surprising. We know it very well. This is nothing else but the Rayleigh's curve. So it's the Rayleigh diffraction limit. It's kind of the resolution limit, which we're very well aware of in all classical systems. Interestingly, however, is that the quantum limit, so if you ask what's the quantum Raman-Rao band, if you allow for all kinds of different methods, shows you that this Rayleigh's course is not intrinsically in the system, but you should be able to do different measurements such that you can overcome this Rayleigh course, and basically tells you that independent of that distance, how broad these distributions is, you can still distinguish them. So it's kind of a super resolution thing. If you ask what you, and here you see also the reference from Zhang, Nair, and Lu, who kind of proposed that. Now, interesting, what you have to do with that is to measure not intensity, but to measure on the fields themselves. Now, quantum pulse gate is doing exactly that. And this is how we did single parameter estimation and frequency domain. And here you see the parameters. So we programmed two incoherent light puzzles. We kind of simulated them. And then we estimated this separation and brought them closer and closer together. For here you see the data for frequency and also for time. And what you can see here is that even the separation is getting very, very small, well beyond the Rayleigh level, where you would say you can't distinguish these, or you can't estimate the separation anymore. These field orthogonal measurements of the quantum pulse gate can do that. And this was for us quite exciting. It really opens a new research route for quantum metrology. Now, in this original proposal, these two emitters had to have exactly the same intensity, and we only estimated the distance between these two systems. But you can generalize that. You can have unequal intensities, you can have the separation again, but the centroid can change. And then you reach a system of multi-parameter estimation. And the question is, how well can you estimate these three parameters simultaneously, and what measurements do we have to do? Here we're working together with Reacek and Louis Sanchez-Zol and others, because it's interesting. This multi-parameter estimation is kind of a measurement uncertainty principle. It's not clear what can be done at all. However, in our latest results with the quantum pulse gate and very programmed measurements, we could show this multi-parameter estimation. This was just published this year in PRX Quantum, and had gained quite some visibility, where you can estimate quite nicely the separation, the centroid, but also these different values. And this is why it's quite nice, because it shows that this quantum pulse gate will also have its applications for measurement-based systems, and we're pursuing this route more in detail. The quantum measurements with adapted gating pulse enabled us to do this very specific research here. With that, I would like to sum up. I showed you different strategies which we follow in my group to really scale up photonic systems, and I think it's an exciting time at the moment. I talked about nonlinear integrated quantum optics, about time multiplex quantum systems, how coherent control can influence the quantum interference. I introduced the concept of temporal modes with PDC states and PM characterization, showed you our work on quantum metrology, and I would like to end up with an outlook. So what's next? What are we planning at the moment? And I indicated already. The next step is we did the engineering these up to now for standard lithium niobate titanium indifused waveguides. The reason why we did that, because there we have highly efficient sources, and actually you need really good systems with very low loss. But as you're probably aware, lithium niobate on insulator has appeared. And this is something where we also had already in Paderborn some experience. And at the moment, we're really getting very much, well, we're developing the technology to do quantum devices on lithium niobate on insulator. And we're making really good progress on the advantage we have. We know exactly how the quantum engineering should work, and also the infrastructure is given there. The benefits is a small footprint, high mode overlap, and spectral temporal engineering, I showed you in the last time, becomes even more important for these systems. I would be interested in scaling up these systems, and we're doing already experiments along that lines, and we're also active in these current initiatives for quantum computation, where we also want to play our part. Up to very recently, it was really very difficult because the resources you need for that is difficult. Nevertheless, we did GZ state generation, so very specific generation of entangled states with time multiplexing, which has an improved scalability. And we do statistical benchmarking of such quantum networks. Now, this is in the direction of photon counting, which I haven't presented here, but we could measure the 10th order correlation function with 64 modes. So we are also already going in that direction and looking for larger systems. And last but not least, I'm very interested in applications. And if I talk here about applications, one of the main interests we have here is quantum spectroscopy with time frequency entangled light. So I showed you already that we have started with the super resolution things, but we also have an ongoing process for entangled photon pair spectroscopies and look how we can use entanglement, engineered entanglement between time and frequency to get an efficient way of two photon absorption experiments and explore how we can use that in such systems. And the other application, of course, is quantum communication with this quantum basket system. With that, I thank you for your attention, but I also would like to thank all the sponsors of their work, and most importantly, my group, because this is not only the work of me, myself, but there's really a lot of very engaged people who are really driven in their research, and I would also like to acknowledge them. With that, thank you for your attention.
Thank you, Christine. I'm clapping on behalf of everyone who's participating. Thanks for this very fascinating look at the quantum world and what is now becoming possible. I think I agree that we are at the verge of something that will really change how our world looks like in terms of quantum computing. And you've nicely demonstrated the various parts that are now being ready to be assembled into larger networks. I would like to start with a question. So in terms of going towards quantum computing, how do you think this will evolve? Like, what is the timeline when we will see maybe even an integrated photonic system where that can do quantum computing and do some sort of, performance quantum computing?
Yeah, thank you for that question. At the moment, the speed is really unbelievable, I have to say. And if you're talking about quantum computing with photonics, we can talk about different ways of computing. I kind of highlighted that boson sampling. This is a fundamental question and just shows you that we can't compute something, but it's not a simulation yet. Now, in this direction, to build up larger systems and try to simulate and understand some effects like combining topological systems and quantum states, this will be in the very soon future and is already done at the moment. So I'm kind of involved in a conversation of the PANS group where it's amazing how many computer scientists are really trying to kind of calculate the classical computers anyhow. Up to now, as far as they haven't done that. On the other hand, you're asking, can I build a universal quantum computer with photonics? And I should be honest, I think up to a year ago, I would have said, well, no, I don't think so. But I don't know if you're aware of that there's millions spent these days in the companies PsyQuantum and also Xanadu, where people really push hard. And I think there's a real chance that we will see in the midterm future quantum computers on that. If this is now the time where it will be decided whether it's feasible or not.
And in midterm is what, 5 years, 10 years?
Something like that, yes, 5 to 10 years. I think if people don't succeed in 5 years, the money will be gone. It's, and you know the initiatives at the moment also. I think in 5 years, we will see how much progress there can be. Let me emphasize, though, one thing which is really puzzling me is that the platforms they're having, they don't have fast feed forward, but we know from the conceptual work or the theory that we need that. And I think this will be one of the breaking points, and we just have one project being granted where we can look in these feed forward things. But I think the development will be really rapid and huge. I expect that simply because of the money which is spent. That sounds, of course, strange, but for this kind of research, it's engineering, where probably a lot of money is needed.
Okay, thanks. I guess we have more time to chat later one-on-one. So I want to open the floor for other questions, and there have been a couple of them coming in already. I would like to remind everyone that if you have a question, please type a Q into the chat channel so that we can then call you up. There have been a few questions by Vikash Kumar. So if you would like to unmute yourself and ask the several questions that you had. Yeah, go ahead.
I have this question, like you have shown about like this temporal modes, basically temporal and frequency bits modes, and that is quasi mixtures. You have shown that. Can it be containing singularity kind of things, and can we export that?
So you kind of want to include donut modes.
Yes, ma'am, definitely that kind of time and frequency donut. Yeah.
Okay, let me say this is frequency domain or not spatial domain.
Yes, ma'am.
I'm not sure. I think the difference between frequency and spatial system is that the spatial is a two-dimensional system. The singularity occurs in the middle of that. Frequency domain is a one-dimensional system. So I don't think that we have direct singularities there. However, I haven't been thinking about that if you can construct something, but it will not be straightforward.
Yeah, yes. And I have one more question, like you have shown about TM tomography. So can it be also like CHSH inequalities there? And can it be advantageous like Bell inequalities?
Sorry, I didn't get that question. So what do you want to do? What do you want to
Ma'am, you have told about like TM tomography.
Yeah.
So can it also contain these CHSH inequalities? Can
yes, well,
there be?
Yes, we have a paper if you're interested in that.
Yes, ma'am.
Temporal modes, a new framework. It's a PRX for quantum information science, and Bell inequalities. All what you know from these standard systems can be done with these temporal modes. And it's even more interesting because you will not have a Bell inequality for two-dimensional encoding, but you can have a multi-dimensional encoding. This is actually one thing which we're looking with colleagues in Düsseldorf, Dagmar Bruce group, where we see how we can understand these Bell inequalities in a finite dimensional Hilbert space, which is not 2, but up to 10 or 11.
Yes, ma'am. And I have just one more question. Like, what kind of modeling can we do for this spectroscopy of this quasi fits, like time and frequency?
This modeling is not easy. This is why we also team up. We started with some naive modeling where we just did put some 2 photon absorption thing, but there's substantial work where people now start to look into resonant and not resonant systems. For example, in Andreas Buchleitner's group, where people seriously look how can we enhance these absorption rates. And I would like to mention, probably you're aware of that nowadays some experiments see an enhancement by using entangled states and others don't. And actually models tells us that they shouldn't see an advancement. My personal opinion on that is that you need engineered PDC states, and not many people know how to do that these days. And if you don't do a very specific engineering of your quantum light, which is adapted to your fluorophore, you won't see the advantage. But this is a research question where we don't know the definite answer yet.
Yeah. Thank you very much, ma'am. Thank you very much. Yeah.
Okay, there's another question by Sven Rogachev.
Yes, hello. I have a rather fundamental question. In regular computing, you have bits. Bits do have only 2 states. In quantum computing, you have more states. Why is this an advantage in computing?
You're talking about qubit encoding, right?
Yes.
This is a heuristic answer, but it gives you some intuition. Don't take me, I know that they are experts, but my personal view is the following. If you want to understand or want to evaluate a joint property of your systems, like you do in a Fourier transform, then the coherence, the fact that you probe all these channels simultaneously is a big advantage, because then you have the encoding in all of them in parallel, and then you get one measurement results only. But if you're looking at a property like a Fourier transform, where you only have a number as an outcome, then this parallelism of the quantum system helps you. Or in other words, where you can see it in these quantum walks, you see that you get much larger spread due to this coherence than a classical system. Now, if you want to probe something which is outside, you're just faster. So it's basically the fact that you're running different probabilities at once. I don't know if there's an answer which helps you, but for your rather vague question, hopefully this is one way to understand that.
Yeah. Thank you very much indeed.
Thanks, Florian.
Yes, thank you for the very nice talk. So I had a question about the adaptive measurements you mentioned in the very end somewhere.
Adaptive measurement is
yeah, just on the last, exactly there. So when you say adaptive, does it really mean that you adapt step by step? So you do the first measurement, you collect a little bit of information, and then based on what you have seen, you choose, I don't know, the basis or so for your next step. Is that what you do? Or
not yet.
So what is adaptive?
Adapted, I think I didn't write adaptive, I hope at least.
Okay,
adapted.
Sorry. Adapted, whatever.
What is adapted here is kind of optimized. We say we have two Gaussian wave packets where we say, okay, we have this centroid, and then depending on the structure of your wave packets. So you know that you adapt these measurements and you have to do that. It's interesting, but what you suggest is the next step.
Okay.
And so if you don't know that, we do compressed sensing and all these things nowadays, and also adaptive compressed sensing. I haven't presented that here yet because it's basically too new.
Okay, thank you.
Okay, Wahid.
Hey, Christine. Thanks very much for the very nice overview of lots of exciting things in the main area that you talked about. I'm going to talk about, I'm asking a question about the very last thing that you had on your very last slide, namely the prospects of doing quantum spectroscopy. Can you say something about what you're thinking of or what you're actually doing these days?
I can. I'm happy to do so. I showed you these temporal modes, right? And I showed you how we can design PDC with very specific time frequency properties. Now, if you choose your waveguide such, and also your pump light, that you can have extremely strong time frequency. So I don't see you, by the way, but time frequency correlations, then you can put this on a fluorophore. And what we're building up at the moment together with size is really the system where we designed a very specific waveguide, which we fabricated, such that signal, idler, photon, both of them are ultra-fast wave packets for itself. So if you look at the marginals, but if you combine them, the correlation times are very short, and also the temporal time is very short, such that if you look at the two-photon absorption, that it fits perfectly in time and frequency. And we are looking at the moment if we get enhanced rate of the fluorophore, of the two-photon absorption, and then the fluorophore system on that. This is interesting because people have tried that with PDC states already. And the funny thing is, if you use CW light for PDC pumping, it appears that they get some advantage. As soon as they use pulse light, and this is experiments which was done at NIST, they don't see anything. But I should say the parameters they use there are more than, well, there's chirps on that, and it's quite critical. You're probably aware that we are collaborating since some time with Mike Raymer. He came up with a lot of theory telling us that this enhancement rate should not be possible at all. However, Nicolas Chesson's Rob Hughes group in Geneva do see these things. And it's quite exciting. And if I look at Mike Raymer's theory, I think the simplification they included are too simplified. Good. Having said that, you probably see this is the real research topic. And then there's at the moment lecture series where people look into that. And we are developing the first system where we really, the quantum light is completely designed to the fluorophore. Because if you don't control the chirp and don't control the timing, I think you just won't see it.
So I guess it's not clear to me what part of it is quantum.
The light. So if you the property of two, if you have look at two photon absorption, you put two individual photons on that. Then
Sorry, you're talking about, so you're sending untangled photons,
Yes.
Okay, so the theory is really so controversial, because that would have been my questions, like, what does the theory say? Because
the theory, I can tell you why the theory is so controversial. The theory is controversial because people consider their PDC only as 2-photon generator. This is not true. You need rather bright sources. So what you have to include is you have to look at the 2-mode squeeze state. And this, it's weird, but you have to have also these absorber properties very nicely done. And this apparently is really hard to simulate if you really take these engineered states and go beyond the first order approximation. And this is why it's, so Raymer's theory kind of predicts no advantage because it's not clear how to deal with that multi-photon component. So they either look at the spectral temporal mode properties for two-photon state where the entanglement is present, but then they kind of don't look what the higher photon numbers are doing, but you have to, because you have to pump the system hard, otherwise it doesn't make sense.
Right, so the question is, I guess, do you actually get to a point where you maintain the quantumness of your light source and pump hard? Is that something that you actually do?
Yes, you do. You do get the quantumness, but you have to have controlled quantumness. So if I pump PDC harder, I still get photon number correlated states. This is this interplay between continuous variable and discrete variable states. So a PDC state which is pumped really hard is a 2-photon, a squeeze state with a 2-mode squeeze state. This is the best thing, but it's not only a 2-mode squeeze state. This is because you have all these different spectral temporal modes. But you have to take into account the photon numbers correctly, as well as the modal properties. And this is why it sounds easy, but if you look into detail, I guess it's not extremely hard theory, but you just have to do it correctly. And
right, but it sounds like what you're saying, if I understand this right, you quickly become multi-parameter, so that the simple kind of 2-photon type I have now is exactly in that spirit. I would have expected just with my experimental kind of gut feeling that by the time you actually do the experiment, all these effects or this real enhancement type of thing will get lost. But you think that you will be able to see a considerable kind of quantum enhancement in a real setup.
Well, it's not only, I think in CW people see it. So if you pump your system up with pulse flight, this is what's done in Geneva at the moment, and we are applying for new.
Do you know what kind of system they look at? Is that a broadband system, or do they look at a kind of a coherent transition? How do they do this?
They look at a broadband fluorophore. Don't ask me which one it is exactly, but a standard fluorophore which is used. But they pump their light source with CW, which ensures for you immediately that you have very strict frequency correlation.
Yeah.
And the timing is also not too far off. But I guess it's not the optimized system yet. So they approached us because they want to have this source engineering to optimize these rates. And I think this is now simply this time frequency correlation, but I think you can do much more if you do shaping and all of these things.
All right, thank you.
Okay, I'm from a very fascinating presentation into interested detailed discussions already. Of course, if we had you here in Erlangen, we could continue with personal meetings, with lab tours, with a nice dinner, etc. So I guess we have to do that at some other time. But what we do have is at least a few individual meetings lined up on Zoom. Christine, thank you very much for this update on your work. I think this is really fascinating. It was a great DLS. So thanks for that. And thanks for everyone else for tuning in. I would like to advertise our next DLS seminar, which is in 2 weeks. with Nathalie Piquet. So if you like this kind of talks, 2 weeks time, same 3 p.m. afternoon slot, Nathalie Piquet. And with that, thank you very much. Have a good afternoon.
Thank you very much.